Okay, so Chem 129. What questions do we have? We're getting ready for final. Finals Wednesday, 1 o'clock. We got about 48 hours to the final. What do we do? What questions do we have? What do we wanna clear up? Yeah.
I was working on homework 2,
Uh-huh.
and there's a problem that asks you to calculate the pH and the pOH, and identify if it's acidic, basic, or neutral.
Okay. So here, actually, Jackie, if you want this chair, I don't think I'm going to sit down anymore.
Okay.
So we want to calculate the pH and the pOH. Great. So there are two equations that we're going to use. What kind of information do they give us to do this problem?
It tells you have 2.55 molar of barium hydroxide.
That's BaOH2? Whoa. That is going to be very basic. Right? Barium hydroxide is one of our strong bases. We know it's going to dissociate. We know that it's got a particular molarity associated with it. It's got a pretty high molarity associated with it. So I'm just going to say 14. Right? Now, let's actually do it correctly, right? So if we do this calculation, there's a couple things that we have to keep in mind. Oh, can you leave it just cracked so other people can still get in? And then hopefully they'll stop being so noisy in a moment. So we want to recognize that we've got pH equals the negative log of our H3O plus concentration. We want to recognize that we've got pOH equals the negative log of our OH minus concentration. We want to recognize that we can do pH plus pOH equals 14. And part of the reason we can do pH equals pOH, or pH plus pOH equals 14, is because we can do our H3O plus concentration times our OH minus concentration is equal to 1 times 10 to the minus 14. 14. Right, we've got, and this is from the autoionization of water, water's equilibrium. So everyone just scoot in a little bit more, backpacks underneath the desks and chairs so more people can fit in. We do want to leave that door open a bit so people know, I know you just want it to be for you, like keep office hours secret so you can do better than them, but I want more people here. So this is the host of equations that we're going to be using. And for me, with the way it sounds like the way the problem is set up, my guess is the equations that we are going to be using the most are this one and this one, right? Because it seems like it's mostly going to be giving us concentrations. We're going to turn those concentrations into an H3O plus or OH minus concentration. We can use this connection to get between the two. We can use water's equilibrium to get between the two. And then we can use the pH equation to get our we can use the pH equation to convert that.
So the question says, note which approximation fails in this example.
Yeah, so, and was this just for this one? This wasn't the one that was a list?
It was just for this one.
Oh, well then I went too far.
Well, it was in the list, but the approximation fails is just for this one.
Okay, great. So let's go ahead and look at this one and see what goes wrong. Now, what range of pHs do we usually expect to get?
0 to 3.
Really, 1 to 13 is where things are typically going to be. Once we start getting to the very acidic or the very basic, there's an approximation that fails. That approximation is already on the board, but we'll talk about that in just a moment. So let's go ahead and do this one. Barium hydroxide, soluble in water, what's going to happen to it? It's going to disassociate. We're going to get barium 2 plus. We're going to get 2 OH minus. Let's do this for 1 liter so it's easy. 2.55 is going to go to 2.55 is going to go to 5.1. Moles per liter, moles per liter, moles per liter. If we're doing this for 1 liter, molarity and moles are the same. So my OH minus concentration is 5.1. I can use this OH minus concentration equals 5.1. I can use that in this equation to get my my H3O plus concentration. So I'm going to do my H3O plus concentration is equal to 1 times 10 to the minus 14 divided by 5.1. That's going to be like 1/5. That's going to be like 0.2. So I'm going to have something that's approximately 2 times 10 to the minus 15. Someone with a calculator. Why don't you have your calculators out yet? My goodness.
I have a question.
Yeah.
From the 5.1, could we just go to get POH?
You could, right? We could also go POH and then do the POH-pH equation. We could go either way.
Okay.
For me, I find it easier to do it this way, and it's also going to be important for explaining which approximation fails.
Okay.
So I picked this way. I prefer doing things in concentration scale because I don't do much physiological chemistry, so I'm not using pH that often. But yeah, you could have done it the other way as well. Making sure it's all readable. Come on in. We can probably leave that door open a bit more now that they quieted down those riffraff. But come in more, come in more. There's space all over up here. So, 2 times 10 to the minus 15 is our H3O plus concentration. We take the negative log of that, and we're going to get something that's like 1.8 times 10 to the minus, 16.1 for our pH. 14.7. I went the wrong direction again. 14.7. Our pH is 14.7. Ta-da! What went wrong? What approximation? Yeah! So notice the autoionization of water has some assumptions here about the H3O plus concentration, the OH minus concentration, and how water is going to interact with this base. Right? At this concentration, the autoionization of water essentially gets broken, right? It's maxed out. Now, there's a couple different ways that we can explain that phenomenon. The correct way to do it is to say activity coefficients of water interacting with ions, and once you go to high enough ion concentrations, there's going to be interactions that we're not taking into account, right? We're assuming ideal solutions where the OH minuses are not interacting with each other. Water can perfectly donate protons, but neither of those things are true. So you're going to run into that problem. This is also, that problem is also referred to as the leveling effect. Right? You hit this point where the acidic or basic behavior of water has reached its maximum and cannot do it anymore. So technically, 14 should be a, to get into kind of the idea of it, 14 should be a pH that we kind of asymptotically approach. Like as we get closer, it gets harder and harder to do that, and then it levels out there. With this type of calculation, we're just doing that. We're just pretending like it's a straight kind of relationship. And that's true as long as we're like in this area. But as soon as we get to the very high or the very low, that doesn't work out so well anymore. And that's the leveling effect. So the autoionization of water starts to break down at very high basic concentrations or very high acidic concentrations.
The problem would you still like show your calculation that way? Or is
Yeah,
there a way to
so
show
you would show this calculation, then you'd say, this doesn't make sense.
Okay.
And then you'd want to explain it, right? Because in this class, particularly in the way I teach 129, I have several calculations where I have you do it, and you get nonsense answers.
Okay.
And the thing that matters to me, because I start to care a lot less about whether you can do calculations or not, and a lot more about how you explain your results and your ability to recognize that your results make sense or don't make sense. right? I want us to start at this point to get away from the kind of like, I have an equation, I plug numbers in, I get an answer mentality. That algorithmic thinking of I follow these steps. And I want to get us into that more like critical thinking of like, well, so what do we expect? What kind of things make sense? What kind of things don't make sense? And how do I build that intuition around like understanding chemistry? And that's going to come in handy when you move on to organic chemistry, because you don't do a lot of calculations when you do organic chemistry, but you have a lot of things where you have to make sense of what's happening. So for a lot of people who don't like Gen Chem, they fall in love with OChem because they're like, I'm not doing calculations, I'm making sense of stuff, and I'm making things, and they love it way more. So if you're like, I don't know about this chemistry thing, give OChem a shot. You might like it. That, or maybe the OChem teachers are just way better than the Gen Chem teachers. I don't know. I haven't taken an OChem class. I don't know. Shall we move on to other questions though? But yeah, the short answer is yes, you would calculate it, and then you'd want to say this doesn't make sense because water's pH should max out at 14. Something has changed. Something doesn't make sense here. Next question.
I had a question on midterm 2. It was the last of the long multiple choice questions.
I don't remember what that is.
If you want to take a look at it, it's like easier to do it that way.
Sure. Is this the how much hydrozonic acid in molarity is left in solution when 45 milliliters of 656 molarity? No, can you read that to me so I can write down numbers while it's being read?
Yeah. So it says how much hydrozonic acid in molarity is left in solution when 45 milliliters of 0.656 molar hydrozonic acid is mixed with 67 milliliters of 0.622 molar sulfite anion. That's pretty much it.
So, I'm kind of wait. No, there's two other important things there.
Oh yeah, it gives you the Ka for hydrozonic acid is 1.9 times 10 to the minus 5. And then the Ka for HSO3 is 1.1 times 10 to the minus 7.
Is 1.1 times 10 to the minus 7. Okay. So, let's talk about problem analysis and how we think about this problem right as we read the problem. You notice the way I set things up and when I was writing down the key information already suggests some amount of thinking, right? I recognize that I have an acid and I have a base, and that this is an acid-base reaction. I've got molarities. I recognize that I've got 2 Kas. What kind of problem are we going to do where we've got 2 Kas and we're asking for a molarity of acid at equilibrium? Is this going to be a simple equilibrium problem? You said the first part, you said the second part.
Huh?
What did you, somebody?
Stoichiometry.
It's going to be stoichiometry and then redissolve essentially, right? So what we want to think about is how this reaction is going to happen. But again, surprise, stoichiometry, equilibrium. So many of our problems. But this one's a little bit different because we can make an overall K reaction for this. So I'm going to have, when I start actually doing the problem, I'm going to have HA plus B goes to HB plus A minus. This is going to have a K reaction equal to this Ka divided by that Ka. So I'm going to have 1.9 times 10 to the minus 5 divided by 1.1 times 10 to the minus 7. That is going to be approximately, someone with a calculator get me the right answer. That's going to be approximately
172.73.
What is it?
172.73.
1.72
No, 172.
times 10 to the positive 2 is what I'm going for. Right? And we could have already kind of guessed that. We got 1.9 divided by about 1. And then 10 to the minus 5 divided by 10 to the minus 7, that's going to be 10 to the positive 2. So I'm getting something around 1.9 times 10 to the positive 2. about 100. So from this, I can already tell that my equilibrium is going to lie very much that direction. That's a terrible looking arrow. Very much towards products, and not just a small amount, but a significant amount, small but significant towards reactants, right? I want about 200 times more products than reactants. Just significant, but it's a non-zero value for this. This is where we have to say, okay, I'm going to make some approximations and hope those approximations work out. I'm going to say 200, that's going to be like all products. That's going to be approximately all products. And we know that's a bad, like, normally when we make that approximation, we're looking at orders of like thousands to hundreds of thousands, and then it's a good approximation. So we know we're making a kind of bad approximation here. 45 times 0.656. But at this point, after we've got this set up, after we've got our K reaction and our starting materials, we are really doing the same problem we did for 8 weeks. 7 weeks. We're doing the same problem we did for 7 weeks. Reaction equilibrium. So I need to get some number of moles because I'm starting with reaction.
0.03.
0.03. Did you give me moles instead of millimoles?
29.52.
Oh,
Okay, and 67 times 0.626?
41.67.
Now, the HA is the limiting reactant. That is to force you to do the equilibrium afterwards, right? If we had excess HA, problem's done as soon as you do the reaction. I wanted to force you to also do the equilibrium. So we're going to have minus 29.52, minus 29.52, plus 29.52, plus 29.52. Zero's here. That's giving us 0. That's giving us 29.52. That's giving us 29.52. And 41 minus 29.52 is going to be, God, why did I pick such ugly numbers?
Got 12.15.
Thank you. 12.15. So at this point, we can say, cool, there's none left. That would clearly be the wrong answer. It's not even, it's almost correct, but factor of 200, there could be like 0.02 left here, and that would still be like a factor of 200, right? So this approximation is not as good. Now, I'm going to see how much redissolves, so I'm going to look at the flip reaction. I don't have any HA to interact, so I'm going to look at how HB and A minus interact with each other. So I'm going to look at HB plus A minus goes to B plus HA. This is going to have what I call K reverse. That's going to be 1 divided by K reaction. So I'm going to have like 4.8 times 10 to the minus 3. Someone help me out.
5.8 times 10 to the negative 3.
I went the wrong direction again. 5.8 times 10 to the minus 3. Is x is small going to work in this case? We're going to be cutting it close. Let's see. So I'm going to need my ice table. I've got some, I'm going to have 29.52 divided by my total volume, 45 plus 67 is going to be 112. A minus, I'm going to have the same number, 29.52 divided by 112. My B, I'm going to have 12.5 divided by 112. My HA is my 0. And I actually need to get these two molarities. So
I got 0.264 for HB and A.
4.264.
And then 0.108.
0.108 and 0. Actually, you know, maybe x is small is going to be okay here. That's about 3 orders of magnitude. Ooh, it's 2 orders. It's about a factor of 100 different. It's not that great for x is small approximation. But let's make the approximation and see how it does. So I'm going to do minus x plus x plus x, approximately 0.264, approximately 0.264, approximately 0.108, and x. I'm going to plug that all in, so I've got 0.108x divided by 0.264 squared is equal to 5.8 times 10 to the minus 3. Solve for x. The same problem, we just keep doing and keep doing. Did I make a note of assume x is small works anywhere on there?
No.
Probably should have. I didn't realize how close I was getting to violating x is small. Excuse me? Let's see, 0.26. I don't know how to. I can't do this.
3.7 times 10 to the negative
3. 0.26 times 0.26 is the one that I'm having trouble doing in my head. 25 times, that's going to be like 125, so that's like 0.12 divided by 0.108. That's about the same. Oh, cool, good. Yeah, so it actually works out okay.
3.
X is small approximation does work. If I look, I'm going to take my smallest one because that's where it's most likely to fail. I've got 0.108 plus 0.1237. You could argue that 0.108 versus 0.105 is different, right? 108 and 105 are different, but we're talking like a 3% error there, right? We're not talking a huge error. So we are within x is small approximation does not fail. Was 3.7 one of the options?
It was 3.04.
Is that the right answer?
Yeah.
So
It's a random.
rounding error someplace? My part, your part, I'm not sure. Is there anything else that we could confuse for? Nothing else is confusable for that as being the right answer.
I think the right answer was actually B, maybe.
I guess I got B and then got it wrong.
Oh, you did? Okay,
Yeah.
that's
Yeah.
what me too. Okay.
0.022 is not the correct answer.
I didn't do the K reaction when I did it, like on the test. So that's where it
Oh, how did you get
I don't know what I
the
did.
K value? It seems like you just made up a K value.
Oh, I just used one.
Oh, you just
KA.
used Ka, right. So this is the weak acid, weak base interaction. So we do have to get a K reaction. And if you didn't get the correct K reaction,
So when did we use K reaction and a weak acid, weak base?
so technically we did, and that's probably where we're getting a rounding error from how I did it, is if we rounded when we got K reverse, we should keep an extra digit there. But essentially, since we have a weak acid, weak base interaction, we have to get K reaction. But then once we have K reaction, all we did was recognize that the K reaction was large. And when we have a large K reaction, we can do stoichiometry. And then we say, okay, but the stoichiometry overestimates because our K reaction wasn't actually that large. So saying we just do stoichiometry is not the best approximation. So we have to go back and correct that. And that's where we do the K reverse. And our K reverse is a small number, so we can use our ICE table and do X is small. And then we get the fact that we do have a correction. It's pretty small, but it's not like 10 to the minus 19 or 10 to the minus 14 small. It's actually a pretty significant amount of this acid is, this acid is left in solution when these two react. That's okay. Just pick it up and pick it up again. There you go. It's okay. So that's how we think about this problem. Notice that the core of the thinking was way at the beginning. Recognizing that it was a weak acid, weak base, and we had to calculate a K reaction was like the bulk of the intellectual work we had to do. After we did that, it was stoichiometry equilibrium. But the bulk of the intellectual work we had to do was right at the beginning. This is the reason that I don't have answer keys for anything. People always get really frustrated by that, but if there's an answer key, it takes away the most difficult part of doing the two most difficult parts. Difficult part number one is figuring out what that first step is. Like that getting started is always like is in my opinion the hardest part. The other thing that I think is really important that having answer keys kind of robs us of is, does our final answer make sense? Right? And having that intellectual thought at the very beginning and at the very end is really what's important. Now, this answer does make sense because when we have a K reaction of like 1.72, we expect all products, we expect very few reactants left. We've got a very small amount of reactants left. So it makes sense. We like that. We could even now at this point, we could go do a check if we wanted to. We could check our answer, and we can do 0.264 times 0.264 divided by 0.108 times 0.0037. Not add, that was just checking if X is small words. That is a weird looking 3. What should this thing in green be equal to? It should be equal to K reaction. It should be equal to 1.72 times 10 to the positive 2. If we don't get that, we did something wrong. Right? There's a check we can do at the very end. I imagine we're going to get about that because that's how we solved it. There might be, again, there might be some rounding errors because the answer I got was just a little bit different. I got something that was about a 10% smaller than what we have. So that could be, rounding one extra digit off could give us that 10% error. Or maybe I didn't round enough and I kept a bunch of extra sig figs. But we still can rationalize our answer. Is that good?
Yes.
Should we do another thing? Who's got another thing to do? Yeah.
Yeah, I'm in term 1. How much hydronium would be needed to change the pH of a 1.13 liter solution from 8.13 to 5.99?
Yes.
I've done this problem like 3 times, and I get a different answer every time, and then I'm alright.
So this problem actually relates to the first thing we did, which was the fact that the autoionization of water breaks down the X's small well, this one is X's small approximation for water's equilibrium breaks down if we're not careful. And so there's kind of this logical step we have to do. I have done this one in office hours. We had it on a quiz. We had it on homework. We had it on the midterm. I'm hoping that people get it now. But let's go ahead and do it. So this is, what's the pH range we're looking at?
Is 8.13 to 5.99.
Now I'm gonna talk about this problem before we do it in terms of the other problems we did. So if we wanted to look at pH going down, if I wanted to look at pH of 5.99 going to pH of 4.37, I'm in acidic conditions. And pH is going down, so add H+, right? That's fine. And I should get a value associated with that. Right? Now, if I looked at the reverse, if I looked at 4.37 to 5.99, I'm still in acidic conditions. Sorry, yeah, I'm doing some thought experiments real quick to explain.
This is where you do like 8.13 to 7 and then.
Yes.
Okay.
We're thinking right now.
Yeah.
We're not doing the problem.
Okay,
We're just
yeah, I was
thinking. Because there's a very common mistake that people make, and I want to explain that common mistake. In this case, pH is going up. What do I add to make pH go up? OH minus. Now, technically, This is going down by the same amount this is going up. So the amount I add to these two should be the same, right? I'm going to add some amount of H plus to make it go down this much. I'm going to add, assuming that the H plus and OH minus have the same concentration, of course, same number of moles, right? I should add the same amount of OH minus to make it go back up to balance it out. If you do this calculation in terms of H plus, it's super easy. If you do this calculation in terms of OH minus, you get the wrong answer, right? Because we're in acidic conditions. Essentially what this means is H plus dominates equilibrium. H plus is dominating the equilibrium of water at that point. So we're going to do this one in acidic conditions. We're going to find the delta H plus, the change in the H plus concentration, and then we're going to recognize 1-to-1 ratio H plus. So let me write this out. 1 mole OH minus per 1 mole H plus. Right? It's a 1-to-1 ratio. So this amount of H plus, that delta H plus, is just going to be how much OH minus I add if I want it to go up. Now, this is for acidic conditions. I'm going to do the calculation in terms of H plus. We can do the same type of logic for basic conditions, where I do the calculation in terms of OH minus. The problem comes when we're actually crossing between the two. And this is a trick. What we're doing is a trick. Are you ready for the trick?
Yeah.
So you said the right thing earlier. So what we have to do in order to do this is we have to recognize that we are going from 8.13 to 7, my basic conditions, plus 7 for 5.99. I have to recognize that this is basic, so I'm going to do it in terms of OH minus, because OH minus is going to be dominating the equilibrium above 7. And then pH is going down, so we're going to be adding H plus. This one we're going to have to use the 1-to-1 ratio. This one is acidic, so I'm going to be looking at it in terms of H plus, and pH is going down, so I'm going to add H plus. So this one I'm going to do in terms of pH, because notice if I did this in terms of pH, I'd be on the order of 10 to the minus 8 and 10 to the minus 7. Right? That's going to be very small. Water's equilibrium is going to actually, we would actually have to go say X a small approximation fails for H plus, we've got to go this other stuff, or we can cheat a little bit, and we actually are cheating a little bit. Well, we're making an approximation. By switching to OH minus, using water's equilibrium, we're saying, okay, X a small approximation works if we think about this in terms of OH minus. So we're going to think about this in terms of OH minus. That's going to save us from solving the quadratic and thinking about an equilibrium. So that means we're going to actually do this one, instead of doing it in terms of 8.13 to 7, we're going to do the 7, 7. Wait, I can't do math. 14, not 9, not 10. 14.
What?
4. 4.877, right? So I wanted to do it in terms of POH. Right? It's going to give us 2. Yeah, okay. I just had to make sure I did that right. And we know that pH plus POH is equal to 14, so I just did that calculation real quick. So I'm going to do this one in terms of that. I'm going to do this one in terms of that. And then I can just add the numbers together because it's a 1-to-1 ratio for H plus to OH minus. And that, I think that's the step that really confuses people, is the first off recognizing whether we're in basic conditions or acidic conditions. and then recognizing that you're still adding H plus and it's just a 1-to-1 ratio. So in this case, in our basic conditions, we're thinking about it in terms of removing OH minus. And in this case, in acidic conditions, we're thinking about it in terms of adding H plus. Question?
The 4.87 should be 5.8.
Oh, thank you. Yeah, 914, thank you. I knew I was doing math wrong. I think I was adding up to like 13. Thank you. 5.87. So if you started doing the problem without checking my math, shame on you. You know my math is bad. But there you go.
Yeah.
What's that?
So your math's usually pretty good.
It's pretty good.
I cannot do that in my head. What's it?
Wow.
No.
Kind of. It was. So honestly, you know how often you make calculator mistakes?
Oh,
Yeah, me in front of the class is actually worse. Because like I feel like I'm in a rush, and if I'm doing it while no one else is doing anything, and like then I'm just like standing there where you're all staring at me using a calculator. I did that like my first year and a half teaching, and I was just like, I can't do this anymore. I keep making typos. No one's checking me, and then I make a typo, and then they're confused, but they're like, well, you used a calculator, it must be right. But when I do it in my head, they're like, oh no, that's not, let me check that, which I appreciate. So that's like. I kind of refuse to use a calculator in front of the class. Because then people believe that I'm doing it right, but like I'm just as prone to make typos on my calculator as all of you. It's part of why I'm like, okay, I want 5 people to say they got this number. Because the likelihood that all 5 of you made the same typo, a lot lower.
All of them were 8 fair game for the
I'd have to double check nothing about rate.
like half-life and stuff.
Half-life and rate's not going to be on there. Should I finish this problem?
Yeah. Why not?
Can you all finish this problem and tell me what the answer is? I'll do it on the board a little bit. I'm sure you can.
Can I send?
Okay.
So I go from 8 to 7 here, but then since it's basic, we change it into POH.
So you're adding. That would usually polarity.
What do we do?
We went into POH, and in that way we're adding the OH to get more specific to get from like lower one to higher one. And that's in terms of POH, and OH, but then since it's a 1-to-1 ratio, you could just change it to H plus.
How do you from
Oh, it's 10 to the negative power of.
Oh, sorry. That's not true.
So we can just do this in terms of molarity. You just do the concentration
Yeah.
of your OH. Because you're
Again, 1-to-1
Yeah.
ratio.
That's your change in your
Um,
OH.
so this
turn
is
on
like
H plus.
Yeah.
And then this
approximately
one
10 minus
is
6.
Yeah.
7. This is going to be 9 times 10 minus 7. This one is also approximately 9 times 10 minus 7. So approximately 18 times 10 to the minus 7 molarity, 1.8 times 10 to the minus 6 molarity. Did I mess up someplace?
I got 2.17
Times
times 10 negative 6.
for your final answer?
Yeah. And the closest one is 2.45.
2.17. So that is because, which problem is this? So I know where that mistake comes from, but I wanted to make sure. Oh, that's okay. I see what I did wrong. This is, I rounded too much. This one's 9.9. This is it's a big rounding error. It's a big old rounding error there. I was like, this doesn't seem right. And this one's 9.2.
What did you get?
So
I did not get
we just
that.
What's that? And you just add them together. Check my work. I want to erase. Is this actually 9.9 times 7 minus 7? And is this one actually? I think. Oh, I totally flipped them. This one's 9.2.
Oh,
This
yeah.
one's 9.9.
Oh,
But double check me.
I got 1.24 times 10 to the negative 6.
I got that too.
For this one?
Yeah.
Oh, why?
I got that if you do it the wrong way.
What do you mean if you got it? Oh, I did it the wrong way?
I think so. Because I did it on the test like that, and I got the wrong answer.
Oh, okay. What do you get for this one?
I got 1.25 times 10 to the negative 6.
Wait, no, that's way different than the first one.
No, I got 9.23 times 10 to the negative.
For this one?
Yeah, that's
what I
right.
got.
Yeah,
Okay.
which one?
That I believe for this one.
It's like you didn't even do it.
Oh wait, I'm confused which one you're asking for.
Yeah, I was just asking for this
Oh,
difference.
okay.
And then just this difference.
Yeah.
Cool.
Then what do you do? Adam.
And then because this is now, keep in mind, this is molarity of OH minus, but we've got a 1 mole H plus for 1 mole OH minus. So we've got a 1-to-1 ratio there. So then this is molarity. Sorry, I don't need to write that. This is molarity H plus. So then if I add 9 to 12, that's where I'm going to get 2.1.
So that's the
2.16 times 10 to the negative 6.
That is my change in molarity. So why isn't that one of the answers?
Because there's liters in the answer.
Ah, yes, I asked for the number of moles, so then you multiply this by 1.13. As long as you keep track of units, it's not that tricky. But if you lose track of units, it's super tricky. But you notice, even if you forget to multiply by 1.13, it's still the closest answer. So you're like, oh, I guess that makes sense. I will say this, if I make my test correctly, that is to say I don't make typos, I don't make any errors, stuff like that, there should be no problems where you need to round 10% to get the answer. Like, you either get the right answer or you don't. It's always tragic to me when people do the calculation and they get the answer of like 2.7 and they round to 3.2 and they're like, well, it's the closest answer. I'm like, well, that's a lot of rounding. But people do that. I will admit I have made pretty egregious mistakes on some tests where it's like the answer is supposed to be 1.06 and I accidentally put the option as 1.6.
Very confusing.
And I feel so bad when I do that, so I try very hard not to do that. Yeah.
I have another problem.
Are we good on this? So like it's really, again, notice the math, the conceptual idea of what's going on, a lot more. Except for apparently I have trouble with the math, but you know. Okay, another question. Wait, was it a follow-up to this before I erased it?
No, it's not.
Oh, thank goodness, because I already erased it. It's like, I guess I can write it all out again. Other questions?
It's 13 on midterm 1. It's what's the pH when 3.42 of a strong base 0.224 molarity? Of 0.224 molarity is added to 100 milliliters of 0.434 molarity benzoic acid. And the Ka is 6.3 times 10 to the negative 5.
And it's 3.42 milliliters?
Oh, it's 3. Oh, why did I say that? It's 34.2 milliliters.
34 point. I might have. I was
okay.
trying to write fast. So 34.2 milliliters. Let's go ahead and do our logical thinking to see if we can eliminate some options real quick. I'm going to do 100 times 0.434 divided by 0.224. Before I even look at the options, I'm going to start thinking. 100 times 0.434 divided by 0.224. It's going to be about 200 milliliters. Let's get the actual number.
What are you doing right now?
I'm finding the volume to the equivalence point.
Oh.
Yeah. 1.93 times 10 to the second. So
193 milliliters to equivalence point. Midpoint is going to be like 80 milliliters. The pH at the midpoint is going to be like oh, I can't do these in my head all of a sudden. It's going to be like 4.8? No. 4.2? What's the pKa?
4.2.
Here's why I did all of this, right? I'm not even doing the problem the right way yet. But remember, the two things that we want to think about is, what do I expect the answer to be? In almost every titration problem, figuring out these three things, the equivalence point, the midpoint, and the pH, gives us a way to think about what the answer should be. 34 milliliters is way less than 80 milliliters. So I am way before the midpoint, which means my pH has to be way below 4.2. So I can look at my options and I can instantly, how many options did you just eliminate?
2.
2 options are straight out. What are the other 2 options that are left?
2.45 and 3.53.
Now, 2.45 is outside the buffer region, right? Because this goes down to 3.2. So even without doing any of the math, I could guess 3.53 without doing any of the problem. Yeah. Half of 193. 193 was the equivalence point. So approximately 80 mils. I didn't get the exact answer. I just approximated. Because it should be 81.5 if we did it exactly correct.
96.
Oh, yeah, jeez. What's 190? I can't do math today. What's 193 divided by 2?
96.5.
Ooh. 96.5. 34 milliliters. I'm actually a little worried that it's not going to be in the buffer region. Let's go ahead and actually, so based off of the information I have, if I wanted something in the buffer region, I would guess 33.53 is my answer without doing the work. Let's go ahead and actually do the work and see what we get. Now, we can do it the shortcut way or the long way. Should we do both and see which one we like more? Let's do the shortcut way. Shortcut way assumes we're in the buffer region, assumes that we can use Henderson-Hasselbalch, assumes x is small is going to work. We're going to say pH equals pKa plus log. My base is going to be 34.2 times 0.224 divided by my acid, which is going to be 100 times 0.434 minus 34.2 times 0.224. I think we're going to not be in the buffer region. This might be a terrible problem. Let's see what we get.
Also, I don't think, wait, this is midterm 1, right?
Yeah.
Have we done Henderson-Hasselbalch yet?
No, so I expected you to do this the other way. I expected you to do it the long way, not the Henderson-Hasselbalch way. Right? We should have been able to do it, but this makes it much quicker. While you're calculating that, I'm going to go ahead and set up the long way over here. The way I expected you to do it would be AJ plus OH minus goes to A minus plus H2O. I'm going to have 34, oops, give myself a little bit more space. H2O plus OH minus, I'm going to have 34.2 times 0.224. I'm going to have 100 times 0.434. I can do the 100, that's 43.4. I don't even have a calculator.
Right.
Oh no, it's like, No, those calculators are. I've got a bunch of broken calculators around the room for some reason. I need to take them to the e-waste place.
I got 3.5.
Oh, thank goodness. 7.0. I might have just broke my calculator. Huh. There we go. 7.66. So, if we use Henderson-Hasselbalch, we get 3.53. Okay. I was worried that I made the problem really bad for a minute. We're still in the buffer region. We still could have done all of our buffer stuff. We didn't know how to do the buffer stuff when we did this problem, but notice just the logic of thinking about it, we technically didn't have to do the problem. We eliminate two options right off the bat. We get it down to a one or the other choice. And honestly, without thinking about it being in the buffer region, which we didn't know about at the time, we'd have to do the calculation to get it between those two choices. With our knowledge about the buffer region, we'd look at this and say 3.53 more likely, right? Oh, the other thing we could have done we could have also calculated the initial pH, right? That would be 6.3 times 10 to the minus 5 x squared over 0.434. We can calculate the initial pH, and I think 2.45 is actually the initial pH. So that would have tossed that option out as well. And just through our logical thinking, we could have not really done the problem. Yeah, the initial pH is 2.28. So initial pH of 2.28, you're adding a bunch of base. You probably go up more than just 0.2. So just from logic, we didn't actually have to do the problem. Now, the way I expected people to do the problem on the first midterm was to do stoichiometry equilibrium. Set up the stoichiometry, recognize that we got an acid reacting with a strong base. That's going to create some reaction. I'm going to recognize that my base is my limiting reactant. So I'm going to minus 7.66 minus 7.66. That's going to give me 43 minus 7.66. Someone help me out with that.
35.7.
35.7 plus 7.66. And who cares about water? 7.66. Notice I can now either go to my ice table, or for those of you that are having trouble with my combined Henderson-Hasselbalch, you can do the stoichiometry and then plug that into the Henderson-Hasselbalch, right? So I'm going to plug these numbers in for my top number and my bottom number. And notice that's in there, 43.4 minus 7.66 on bottom, 7.66 on top, because I'm going to be looking at the reverse equilibrium. No, I'm going to be looking at this equilibrium still, not reversing it. Products over reactants. If we kept going with this, then I would set up my equilibrium of HA plus H2O goes to A minus plus H3O plus. I would set up my ice table. I would have 35.7, don't care, 0, oops, sorry, not 0, 7.66 and 0. I would have to divide by total volume to get it to molarity, which is going to be 134.2. I'm going to do minus x plus x. And I get 35.7 divided by 134.2. And I'm going to get 7.66 divided by 134.2 and x. Solve for x there. Notice there's a lot of the shortcuts that we learned about. I said there were like 4 important shortcuts. We went over them when we were first doing these problems after the midterm. Ratio of concentrations, that 134 is going to cancel out. Ratio of concentrations is the same as ratio of moles. X's small approximation allows me to ignore the entire ice table and just take the excess step of my stoichiometry. So I don't need to do the ice table at all at this point for these types of problems. My amount of weak acid after reaction is equal to the amount of strong base I added, right? That's that number. My amount of weak acid left over after reaction is the amount that I started with minus the amount of base I added, right? Those shortcuts allow us to jump to the modified Henderson-Hasselbalch right away. Saves us a lot of time if we understand all of those concepts going into it. Wasn't that fun?
Yeah.
I mean, so here's my favorite thing about like office hours during finals and like talking about this stuff. Is if you think back to the first like solubility problem we did where we just had a solid dissolving in water and how that was like, whoa, what's going on? But now we can like do this. Like this is the point where I can look at like all of you and be like, oh, we figured out a lot of stuff this quarter. And we've actually come a long way. It's exciting. I'm gonna get all choked up. But before I do, what other problems should we look at?
I have a kind of definition question. When a weak acid reacts with a weak base, the equilibrium favors production of the weaker acid. Is that right?
Yes.
Why?
And did you say that was a dumb question?
No.
What did you say?
Definition.
Oh, definition question. This is perhaps, if you ask some of my colleagues who teach organic chemistry, this is perhaps the most important question in all of 129. I disagree with them a little bit, but this is kind of one of the defining principles of how we can think about a lot of reactivity, especially if we go to the Lewis definitions of acids and bases, where we're talking about electron donors and electron acceptors to form new covalent bonds. You can essentially talk about all reactivity in terms of acidic behavior and basic behavior between two compounds. So, when we want to think about this in terms of a weak acid, weak base interaction, we're going to go ahead and say HA plus B goes to HB plus plus A minus. This is a weak acid. This is a weak base. This is a conjugate acid. This is a conjugate base. I can also think about this reaction in reverse, correct? I can think about HB plus A minus goes to HA plus B. In this case, this is the weak acid. This is the weak base. This is the conjugate acid. This is the conjugate base. The question becomes, which way does this reaction actually go? What's actually going to happen? Which product is going to be favored? Is it mostly going to stay as HA or is it mostly going to stay as HB? And what I'm looking at here is how well does this compound give away protons versus how well does this compound give away protons? And that's not going to be like two separate reactions. It's going to be the two reactions kind of going back and forth. So, for example, let's say that HA is the stronger acid. Every time HB tries to give it a proton, it's going to give it right back. Right? Every time that gives it a proton, it's just going to give it right back. My equilibrium is going to lie towards HB+. You could do the same logic for the other way, but essentially, the stronger acid is going to be better at disassociating. It's going to be better at donating protons. The weaker acid is going to be less capable of disassociating, less capable of giving away protons. So the strong acid will always push towards the weak acid being formed until you get to equilibrium, of course. Now, what we have to be careful about is if we just mix a weak acid with a weak base together, we have to establish equilibrium. So the reaction will still happen, but we're going to expect when equilibrium is established that we have more products than reactants when equilibrium is established. Does that make sense? So it's
Yeah.
not it's not actually a simple thing. When we like I went through this logic with all of you, and then I was like, the easy thing to remember is the weak acid is like the favored. But notice there's a lot of thinking, there's a lot of detail, there's a lot of context to that thing that you just remember.
So kind of along the same lines. If you guys are ready.
Yeah, I think everyone ready to move on? Great, let's go for it.
So just a general question that I have is like, how can you tell when changes in the pH are going to affect solubility?
This question. So this was on the homework. This was on a quiz. This was on the first midterm. This was on the second midterm. And
I've been putting it off for a while.
Today's the day.
I put it on the second midterm being like, I'm sure they got it by now. I'll give them free points. I was like, I almost took it off. I was like, this is going to be too easy for them now. And like still, like 75% of the class got that problem wrong. And I was just like, wow. Okay, so when we think about this, there's a couple different ways we can think about it. Again, we have our magical phrase that kind of is the shortcut. The thing we're doing let me think if I can think of another one.
Are you the one from the test?
No,
No.
we're doing weird stuff.
I'm doing weird stuff.
I'm gonna do a bunch of silver things. There. Okay. Which of these will have their dissolubility affected by pH?
The ones that form weak acids.
Yeah, exactly. AgCl, will it form a weak acid? Nope, not that one, right? This is going to, upon the addition of H+, would form HCl, strong acid. That means that wouldn't happen. It would go back the other way, right? Not going to have any effect. Right, AgNO3. HNO3, strong acid. HCO3, weak. HClO, weak. HSO4, minus.
It has like 2 steps, right?
This one is a little bit tricky. I put this one last for a reason. I was trying to think of something where it was Ag2. H2SO4 we always tell you is a strong acid. Technically, only the first proton is strong. The second proton is a very, very good weak acid. Its pKa is like 1.1 times 10 to the minus 2, so it's or like something along those that lines. It's a pretty strong. It's a pretty good weak acid. Technically, this would fall in the weak-ish category. So, in terms of will it have an effect or not, this would have a slight effect. And I haven't asked any problems where you actually get to that level of detail. However, we are now at the point where we could actually not just say whether there's an effect or not, but we could also calculate the effect by looking at the way we should be looking at all of these. I'm going to pick AgClO for how we would look at this if we actually wanted to calculate it. So the shorthand is, in practice, we are looking for, and the phrase that I like to use is, if the anion of the solid is the conjugate base of a weak acid, a decrease in pH will affect the solubility. Just to say, if you're making a weak acid, you've got some equilibrium phenomena you have to worry about. And I forgot a minus there. So let's look at AgClO and talk about how we can actually quantify this idea as well. So if we looked at this, we would say, we're going to look at it in 2 steps. We'd say AgClO is going to have some equilibrium to go to Ag plus ClO minus. This is going to have some KSP associated with it. And then I'm going to have H plus ClO minus going to HClO. Now my question is, how much is this going to form? Because this forming is what's going to affect this solubility. Right? This is going to have, is not, if I write Ka for this, am I correct or not? Is this a chemical reaction for a Ka? What should I write? 1 over Ka. So when I put these, that's a weird one. There we go. So when I put these two together to look at my net reaction, I'm going to have AgClO plus H plus goes to Ag plus ClO minus. This is going to have a K reaction equal to KSP divided by Ka. Oh, yes it is. Thank you. Lost track of what I was doing. This, and now we really do need states. I was avoiding states of matter, but we need states of matter here. So now, if I have a large K reaction, I can do a stress and ice. I can do a stoichiometry equilibrium. If I have a small K reaction, I can just say that I can jump straight to the ice table. But notice, this K reaction, when we did our KSPs, it was just like two things times each other. My K reaction is going to be products over reactants. It's going to be the Ag plus concentration, the HClO concentration, divided by the H plus concentration. So if the K reaction is small, I would just do like a, forget the Ag plus, I'd have like a minus X plus X plus. I'd have a minus plus plus, and I would go through and, you know, calculate it.
What are we solving for here?
I'm just doing a theoretical kind of like, how could we actually take into account the way that acid affects solubility? So we would be calculating like how much silver ion ends up in solution.
Okay.
Because that would tell us how much the H plus affects the solubility, right? So if the H plus, if we get the same amount of silver ions in solution as we did for the regular KSP, there's no effect on solubility. If we get much more, then there's clearly an effect on solubility. Chances are, if we looked at the KSP and the Ka for this, we would have to do a stoichiometry table and then an ice table to figure out how much this affects it. But that's how we could actually put numbers to it. Yeah. Cool.
I have another question. Oh, she has a question.
Just to like clarify if it was opposite and it was like which solid will have its solubility impacted by an increase in pH, it would just be.
I don't like that problem. I'm going to take that problem off the homework because the increase in the pH actually has two really important phenomena that are very different than this, right? So three important phenomena. First off, an increase in pH can be thought of as a decrease in your H plus concentration. So you can say, how does a decrease in H plus concentration affect the equilibrium, right? That should be a small effect, right? That should not really affect it. Even if you have a weak acid, taking away H plus just means those ions are there even more, so that shouldn't affect it. If you have the OH minus interacting with the cation, the metal, you have to consider whether you're making a hydroxide solid and what's the solubility of the hydroxide solid, and that could have an impact. And then you also have the formation of metal complexes. That could also happen, right? If you have OH minus, you could form an AgOH2 metal complex, and that could also have an effect. So it's much more complicated than the decrease in pH kind of acid-base equilibria thinking. So I'm gonna move that problem to like the last homework when you know metal complexes, and it's gonna be like this kind of like nice, talks about a lot of different things, but it is significantly more complicated. Yeah.
So basically, if you form a strong acid, there's going to be no effect.
Yeah. Right. So, and the rationale is, so if I change this from HClO to HCl. Let's do this real quick. Let me change the color so we know that we're talking about something different for a second. If I change it to AgCl, Cl minus, so I'm looking at H plus Cl minus goes to HCl, and I'm looking at the Ka here. What's the K, or 1 over the Ka? What's the Ka for HCl? It's not 1. It's like 1 billion. Oh, you were pointing up. I was like, 1? No, but like high. So let's say it's like 100,000. So it's like 1 times 10 to the 5. What's 1 over the Ka? 1 times 10 to the minus 5. Right? It's going to be some small number. Now, I'm going to be taking my KSP, which is already a small number, and I'm going to essentially be multiplying it by an even smaller number. Now, if you do that, you're going to get some sort of weird like secondary effect of like, oh, it's going to be putting more Cl into solution. That's only if you're adding actual HCl. So if you continued on from this, you would start to make some mistakes because it looks like more Cl is appearing. What's happening here is essentially this step here tells us we don't form HCl. If we don't form HCl, we're not affecting the Cl minus concentration, so we're not affecting the AgCl. That is different. So the trouble you get into is if you step forward and you do this calculation, this 1 times 10 to the minus 5, multiplying to get your K reaction, would be saying essentially what happens if you add HCl. If you add HCl, the Cl is going to interact with the Ag plus and form more solid. So it would actually push to making more silver chloride. But you have to be careful because you're not actually adding HCl. You're adding H+. You're probably adding nitric acid to avoid this problem. This is also in lab. If you remember when you were doing the, there were a couple tests where you were specifically not using HCl. That's because Cl will interfere with your test and like precipitate out when it's not supposed to. So you had to use nitric acid, or you had to use, I think you had to use perchloric acid. You had to use like, or chloric acid at some point. You had to use some weird acids for some of the tests, specifically to avoid, and there were some places where you couldn't use sulfuric acid, again, because the SO4 2- would have caused precipitation. So it's one of these things that like we don't really think about a lot of the time when we're talking about doing reactions. We're like, oh, just add an acid. What acid should you add? And it's like, oh, let's just add any strong acid. But you actually have to think, hold on, HCl and HNO3, even though they're both strong acids, have different reactivities because of the anion, that counter ion that's there. And they can really mess up your reactions. You actually have to pay attention to what we call side reactions and things, unintended things that could happen. Nitric acid is usually a safe choice because nitrates are always soluble. But you also have to be careful because nitrate, NO3- is, it gets reduced, right? It can go through a redox reaction. So you also have to be careful about that. If you remember when you were doing your bromine test, you actually added nitric acid at some point, or like couldn't add nitric acid at some point to cause a redox reaction. So like you also have to be careful. There's like all these little things that could happen. So like Cl is, you know, not very good at going through redox reactions, but nitrate is. So you gotta be careful for that too. So that's why in a lot of the problems I'm just like, let's just say H+, right? How much H+ would you add? We're not going to worry about how the H+ gets in there. We're just going to decrease the pH. I'm not going to say how because there's all these side reactions that can get in the way. But how much would you decrease the pH? So, and that just gets to the fundamental problem of doing chemistry on a board book versus doing chemistry in the lab. Let's see. I'm looking at the time. We got like 10 minutes left. So other questions? We got about 10 minutes to do more questions. Yeah.
Going, so I just want to not talk about like super chemistry based, but like so basically what happens is because it's 1 over Ka with the formation that's favoring the formation of CLO.
Yes.
Taking CLO out of the thing, so it's favoring this solution.
Yes.
Okay.
Exactly. Exactly. That is the logical way to think through it. You are if you have a weak acid that can form, you are removing the anion, which means the solid has to fall apart more based on the Chatelier's principle.
Okay, so
Exactly.
decreasing pH when it forms a weak acid increases the solubility of the
Yes.
I have a question.
Yeah.
It's from worksheet 4.
Sure.
And it asks, how does the addition of Cn minus impact the solubility of AgCl?
Ooh. So that by itself is hard to tell what's going on. So we're asking, how does Cn minus affect the solubility of AgCl? Do I give any hints or notes in there?
No.
Oh, I do. Which problem is
You do?
this?
1.
Oh, I don't. What a shame.
What a shame.
So there's some other information that we have to have in order. This was on worksheet 1?
4.
Oh, worksheet 4. Yes, that does make sense.
Do you need the KSP with AgCl and AgCN?
Yeah. Oh, it's even more than that. So we got the KSP of AgCl. We can look at the KSP of AgCN, but really we've got a KF of AgCN2 minus. So there is this thing that is very likely to form. I don't think you even have a KSP. I'm not even sure if there's a KSP for AgCN. I think any excess CN, it pretty much automatically goes to this unless you've got like just the right concentration of CN minus. But you're most likely to be looking at the formation of a metal complex. So that question is not that great because it doesn't give you any hints at the fact that there's the metal complex formation. That's why I asked if there was a hint. So like normally I would give like, no, the KSP for AgCl is this and the KF for AgCN2 is this. And the fact that you can form a metal complex is going to tell you that.
So it wanted to form a metal complex, so just missing some information. Or
So the formation of a metal complex is going to give an apparent increase in solubility. Right? If we can form a metal complex that's going to bit silver ions into solution, which means that this thing is going to look like it's becoming more soluble. So that problem should give some hint at the fact that a metal complex is capable of being formed there. Dicyanoarginate is one of the most common examples, though. This is dicyanoarginate.
okay.
Question.
That's because the formation constant of what is it?
Dicyanoarginate?
Dicyanoarginate it's so large that it increases the solubility
Yeah.
of AgCl.
The KF, remember the KF values are always super big. They're always like on the order of 10 to the 12. We actually also, and this is perhaps why this question is super fair even though it doesn't have the hint. This is exactly what you did in lab for the chloride test. You formed a silver chloride precipitate, then you dissolved it by adding. Oh, I think you did the diamine. You did the NH3 complex, not the CN complex.
But it's the same.
Same concept, same idea. It's just less dangerous.
Cool.
Ammonia is less dangerous than cyanide.
So wait, it's decreasing solubility of, it's increasing solubility of silver chloride?
Yeah, so when we look at this, if we looked at the KSP for this, this is on the order of like 1 times 10 to the minus 17. This has KF on the order of 1 times 10 to the positive 15. So if I look at this overall reaction, if I looked at the silver chloride by itself, it's really insoluble. Not very much solid falls apart. If I look at it with the cyanide, and I shove 2 there to balance it, I'm going to have something like 1 times 10 to the minus 2. My equilibrium is still reactant favored, but a lot less reactant favored than it used to be. So I'm going to see a lot more silver dissolving than I did before. And these are approximate numbers. I could be off by orders of magnitude, but it's a really small number, a really large number.
Is it going to dissolve and then immediately form the solid?
Which solid?
Is that not a solid? Okay.
No. So, and this is one of the powers of it. Ions don't form solids,
yeah,
right? Yeah.
Yep.
So that's going to be aqueous, solid, Aqueous. Goosh. States of matter matter so much. Yeah.
And if we were to just like, I'd say like find the concentration of the dicyanoarginate,
Yeah.
you just use the K reaction.
Yeah, and then it'd be like the same problem we did where you're gonna do some like reaction between these two, and then some equilibrium. And in fact, with this number, 10 to the minus 2, you might be able to just step to an equilibrium step.
I have another question.
Sure.
It says which complex is likely to have a square planar geometry, and then there's a list of them.
Yeah, so which complexes are likely to have a square planar geometry? So remember, square planar is one of our unique exceptions. Pretty much everything loves to go octahedral. And then we learned our special exceptions that go tetrahedral, square planar, and linear. And the ones that went square planar, do you have a periodic table handy?
No.
So I look on the periodic table and I can tell which ones go square planar.
D10.
Oh,
D8.
D8, there we go. So nickel 2 plus, platinum 2 plus, is it palladium? PD?
Yeah.
Palladium 2 plus. Those are the ones that are likely to go square planar.
Okay. It's like one of the options. I didn't know if it was like the ligand or coordination number.
Yeah, oh, so this one, okay, this one is almost silly. I'm going to show this to everybody. There you go. I don't think you can see that. Probably wasn't in focus. So we can also tell the first one has a coordination number of 6. That's going to be octahedral. The last one has a coordination number of 6. That's going to be octahedral. So we're just looking between B and C. That's the zinc. That's the tetra aqua zinc or the tetramine platinum. And so it's just which one's going to go square planar, which one's going to go tetrahedral. The zinc would go tetrahedral.
Oh, it's A6 because of the
Yeah, the ethylene diamine is a bidentate, so that's going to have a coordination number 6 each ethylene diamine. So what was that compound?
MnEn2, NH3 2, and then the overall charge is +2 plus.
So this would be diamine, bis-ethylene diamine, manganese.
How come, like, why do
2+.
you use di versus bi? Like, when do
Bis.
When do you use bis?
So you use bis when the ligand already has di in it.
Oh.
Because if you say diethylene diamine, that could mean 2 ethylenes and 2 amines. But you want ethylene diamine as one ligand.
So it's diamine, bis, ethylene, diamine.
Yeah, so notice, this is diamine, bis.
Why do you put diamine twice?
I didn't, and that's the trick of the bis. So when there is bis in the name, it means the next di is part of the ligand name.
Oh.
So ethylene diamine is all one ligand.
Okay.
That's what the EN is abbreviating.
Oh.
But
Okay.
if I put diamine, diethylene diamine, it would look like I've got 2 amines, 2 ethylenes, and then 2 more amines.
Okay.
So the bis is our clue, is the signifier that the next Greek prefix is part of the ligand name.
Wait, I'm still confused where the first diamine comes from.
NH3.
Oh, okay.
Yeah. It's just a weird compound that has diamine and ethylene diamine in it. So if I were to build this, I think I've already got something that looks like this. It would look like this. This would be diamine, and this would be our ethylene diamine, ethylene diamine. And this is what it would look like. Octahedral, and this would be the cis version. We could also have the trans version. And then we could talk about whether it's the Rausch or the sinister, the R or the S, for its optical isomer as well.
So if you wanted,
Did we go over R and S like sinister?
No, I would
Okay.
just say does it have an optical isomer or not.
Okay. And
That, but you're going to do that in
that's like the
organic
mirror
chemistry.
thing?
It's the mirror images,
Okay.
right? Does it have a mirror image?
So for the oxidation number, would manganese have a charge of 2?
Yeah. Sorry. I'll finish. And sorry, I should say non-superimposable mirror image thing.
Okay.
So yes, and it has a charge of 2 because the ethylene, diamine, and the amine are both neutral ligands. So they would not put extra charge on there.
And is there space between the diamine and the cis?
There should not be. This is just because, like, even though I love these names and I think it's hilarious that they're one word, I still accidentally put, and also you should not capitalize the M in manganese there because it is still just all one word, and you don't capitalize letters in the middle of words, even though this word is actually a string of words. Oh, the silliness that is naming metal complexes. Okay, I'm gonna check real quick and see if there were no questions online, so I guess that's it.